Welcome back. Today we're going to talk about projectile motion. And projectile motion means the motion of an object that has been projected and is flying through the air freely, and only gravity is acting on it and nothing else. So no air resistance, no other forces, nothing is stopping it, only gravity is acting. So let's write that down. So the important thing here is that if the only force acting on the object that was projected, or the projectile, we can call it, is gravity, then there's only going to be acceleration due to gravity. So there's no acceleration horizontally, only acceleration due to gravity. So basically the acceleration is negative 9.8 meters per second squared downwards. So projectile motion can look two different ways. It can either look like something that starts going off in diagonal, comes up to a high point, and comes back down, and the projectile ends up here later. Or it can look like an object that was dropped from something high, like a table or something. It went horizontally, and then gravity started acting on it, so it falls down sort of like a semi-parabola. So this one we call projectile motion. And this one we call semi-parabolic motion. Hopefully you remember from math class, a parabola is a function that looks like a curve that comes back up, or that goes up and comes back down. It has a maximum point. So in semi-parabolic motion, we start at the maximum and we only have half of a parabola. And in projectile motion, we have the two halves. We have the top, which is the maximum, and then it goes down on both sides to the same distance. And it's exactly the same in the first half and in the second half. It's like a mirror image of each other. So what you can notice here is that we only have acceleration due to gravity, which is vertical. So there is an acceleration downwards, but there's no acceleration to the right or to the left. So if we want to use our kinematic equations, our equations of motion that we learned a while ago, that had acceleration, speed, displacement, time, then we probably need to divide the problem into horizontal and vertical. And that's what we're going to have to do every time we have a projectile motion or semi-parabolic motion exercise. So the first thing we need to do is make sure that all of our variables are either vertical or horizontal and not in the middle. So let's look at semi-parabolic motion first. So what do we know about semi-parabolic motion? So we know that the acceleration in y, so we're going to call it AY, or the vertical acceleration, is negative 9.8 meters per second squared. We always know that. But the acceleration in the horizontal direction is 0. It's always going to be 0 because there's just nothing stopping it in the horizontal direction. But what else do we know? We know that the initial velocity, which is this one over here, is only to the right. It's just to the right. So the initial velocity in the vertical direction is 0. It's 0 because there's only a velocity in the horizontal direction. And what do we know about the velocity in the horizontal direction? It's constant. There's no acceleration, right? No acceleration in the horizontal direction. So the velocity in the horizontal direction is constant and it will never change. So what will happen to this ball? It's going to go, and initially it'll only have a velocity to the right because that's the initial velocity. But as it moves forward, it's going to start acquiring a velocity downwards as well because there is an acceleration. So the initial vertical is 0, but as it goes forward, it's going to get more and more of a vertical velocity. And when it hits the ground, the vertical velocity will be even greater than the horizontal velocity that was not changing. But there will always be a constant horizontal velocity as well. And the last thing that I want to remind you is that time doesn't have a direction. So even though acceleration, velocity, and displacement have directions, time will never have a direction. So we don't call it tx and ty because they would be exactly the same. So we just call it t. t is just the time in both directions, and it's exactly the same. So when we start working on equations and solving equations, the time that we use for all equations, vertical and horizontal, will be exactly the same time. Now that we've seen semi-parabolic motion, let's move on to projectile motion. So what is the same in between projectile motion and semi-parabolic motion? Well, first, the accelerations are the same. So again, we only have acceleration due to gravity, so it's only vertical acceleration, and it's negative 9.8 meters per second squared, and the acceleration in the horizontal direction, as always, is 0. So that stays the same, doesn't matter which problem we're looking at. However, the initial vertical velocity is now not 0, because notice in this arrow over here, it doesn't go exactly to the right as it did here, but it also doesn't go exactly up. So what we're going to have to do here is use what we learned about vector components to decompose this vector of velocity into its horizontal and vertical component. So what we have here is an initial velocity that we're just going to call VO, and we need to divide it into VOX and VOY. So let's do the triangle like we used to do. This is VO, and we need to know here and here, this would be VOY, the vertical velocity, and this is VOX, the horizontal velocity. So what we learned before is that in order to calculate those, we need to use cosine and sine. So the VOX was always, if we have this angle down here, so this angle we're going to call theta, and it's down here, then the VOX is the VO times the cosine of theta, and the VOY is VO times the sine of theta. So always when we get an exercise about projectile motion, the first thing we need to do is identify the angle, which we're going to be given. The angle is always a given. And with that, calculate the initial vertical and initial horizontal velocity. So once we have those two, we can use them to solve the problems. And again, the VOX will always be constant. The VOX is constant because the acceleration in x is 0. So once we calculate that Vx, it's going to be that for the whole motion. Instead, the VOY is going to be 1 at the beginning, and it'll start getting slower and slower as it gets to the top. So because gravity is acting against the ball or the projectile, as it goes up, as more time passes by, the velocity in the vertical will get smaller and smaller. And once it gets up here, the velocity in y is going to be 0. Why? Because the ball went up and it had to stop at the top so that it could change direction and start coming back down. So once it passes from the maximum point, we're going to call this the maximum point, and it starts coming back down, the velocity will start increasing again in y, but downwards. So it's going to become a negative velocity. And the fun thing about this is that because this half was exactly the same as this half in all conditions, then the velocity here at the end in y will be exactly the same as this one, but negative. So the whole deceleration that happened here is going to be the same acceleration that happens here. So basically, while the VOX stayed constant, the velocity in x stayed constant, the final velocity in y will be equal to the initial velocity in y, but negative, because now instead of going up, instead of being this component up, it's going to be a component downwards. Now, another thing to remember, as happened in semi-parabolic motion, there's no tx and ty because they would just be exactly the same. But an interesting thing that happens in projectile motion is that the time that it takes to go up, so the time that it took from here to here, is exactly the same time as it takes from here to here, because it's a mirror image of each other. So time to max point is equal to the time from max to end. Right? So if you already calculated the time from here to half of the trajectory, then from the half to the end, it's going to be the same time. A couple of definitions as well that can help you in case you don't know. Trajectory, that I've been using, means the path that a projectile takes. Trajectory is just the path. So this dotted line here would be the trajectory of a projectile, and this dotted path here is the trajectory in a semi-parabolic motion. That's trajectory. And the other important word is called range. Range is the horizontal distance. So basically, remember that we have two other variables that we haven't really talked about. We have the displacement, the horizontal displacement, x, and we have the vertical displacement, y. So the range is equal to the horizontal displacement. So basically, the range here in semi-parabolic motion is this distance between where the ball was at the beginning in x and where it fell. So this is the range, so let's call it r or x. And in projectile motion, it's the horizontal distance between the beginning and the end. This is the range r or x. And the displacement y would be, for semi-parabolic motion, this height over here, this would be y, and it's probably going to be negative because it started higher than where it ended up. And for projectile motion, the y is going to be 0 from the beginning to end, right? Because it ends at the same height. So if here it was at 0, it goes up to a maximum height, so this can be the y max, and then when it comes back down, the y is equal to 0. Right at this point, the y is equal to 0 again. So if you want to know the maximum height, it would be this distance from the horizontal ground to how high it gets, but the total height at the end is coming back and becomes 0 again. So maybe you're wondering, and you're going to figure out in today's class, what is the angle that you would have to throw a ball or a projectile in order to get the biggest maximum height? So suppose you were going to throw it at 5 meters per second. Do you want to throw it at 30 degrees? Do you want to throw it at 45 degrees? Do you want to throw it at 60 degrees? So what gives you the maximum height? You will see today. And what gives you the maximum range? What if you wanted to get as far away as possible? Would you throw it maybe at 5 degrees so that it goes more to the right than upwards? Or would you throw it maybe at 85 degrees so that it goes up and, I don't know, maybe gets farther? So you're going to figure out, hopefully, the angle that you need to get the maximum height and the angle that you need to get the maximum range. And next time, we're going to look at how to solve specific equations to solve problems for projectile motion and semi-parabolic motion.